Have you ever wondered how we could make trillion parameter models feasible for local use by hobbyists within a year? As mind-boggling as it may sound, recent advancements in quantization techniques may hold the key to unlocking this possibility. First, let's delve into the realm of sub-bit quantization. This technique pushes beyond the conventional 1-bit or 2-bit quantization methods. Instead, it seeks to represent weight values with fractions of a bit, without causing a significant drop in model accuracy. Now, why is this important? Well, it's simple. By reducing the precision of the numbers used to denote model parameters, we slash the storage requirements dramatically. This could potentially allow colossal trillion-parameter models to snugly fit into the memory constraints of high-end consumer hardware, something that was unthinkable until very recently. Moving on, let's turn our attention to adaptive and dynamic quantization. This is an exciting development in the field of quantization methods. As the name suggests, these techniques can adapt in real time to the specific needs of different parts of the model or to the data being processed. Imagine a chameleon changing its colors to blend into its environment. That's essentially what adaptive and dynamic quantization does. It optimizes the balance between performance and accuracy on the go, using higher precision only when absolutely necessary. These developments represent a significant leap in our quest to make complex AI models more accessible and efficient. By harnessing the power of advanced quantization, the dream of running trillion-parameter models on your home computer is no longer a far-fetched fantasy. But remember, this is just the tip of the iceberg. There's an entire ecosystem of hardware innovations, algorithmic efficiencies, software optimizations, and community contributions that play a critical role in making this dream a reality. By pushing the boundaries of quantization, we can start to imagine a world where trillion-parameter models run on your home computer. So, buckle up and join us on this thrilling journey into the future of AI. Advanced quantization techniques are just the start. To truly make trillion-parameter models a reality, we need hardware innovations. Our journey begins with specialized AI processors. You see, the next generation of tensor processing units, or TPUs, and field-programmable gate arrays, known as FPGAs, are being tailored to handle these quantized models. These aren't just your run-of-the-mill processors. They're like the supercars of the AI world, designed to provide the computational efficiency necessary to run these models in real time on local machines. Just imagine having the power to process billions, even trillions of parameters right at your fingertips. That's the promise these specialized AI processors bring, but the innovations don't stop there. Enter neuromorphic computing, a fascinating field where chips are designed to mimic the neural architectures of the human brain. These aren't just any chips. These are chips that could potentially revolutionize the way we handle large models. Their inherent ability to manage sparse and quantized data makes them uniquely suited to this task. Think about it, our brains are the ultimate processing units. They're capable of handling complex tasks with incredible efficiency. If we can create chips that mimic this, we might be able to run extremely large models much more efficiently. The potential of these hardware innovations is immense. Specialized AI processors could provide the raw power needed to handle the computational demands of trillion-parameter models. Neuromorphic chips could offer a way to handle the complexities of these models by leveraging their natural ability to process sparse and quantized data. These advancements are not just exciting, they're revolutionary. They have the potential to change the way we think about computing, to push the boundaries of what's possible. With the right hardware in place, the daunting task of running trillion-parameter models locally becomes less of a pipe dream. It becomes a reality that's within our reach, a reality that could redefine the world of AI as we know it. Hardware alone can't solve the problem. We also need to improve the efficiency of our algorithms. Imagine a city. Now, imagine you're trying to map out the shortest route to visit all the landmarks. The more landmarks, the more potential routes, and the more complex the problem becomes. This is analogous to the challenge faced in running large neural network models. The landmarks are the model's parameters, and the routes are the computations needed to process them. The key to solving this complexity lies in algorithmic efficiency. One effective approach is leveraging sparsity in neural networks. Sparsity in this context refers to the fact that at any given time, only a small portion of a neural network's parameters are actively being used. By focusing computation on these active parameters and skipping the rest, we can significantly reduce the computational load. It's like identifying the landmarks that are closed for the day and removing them from your city tour. But sparsity is only half the story. The other half is designing efficient model architectures, which are optimized for quantized operations. This means building models that perform well even when the precision of their parameters is reduced through quantization. Think of it as designing a car that can run efficiently on lower-octane fuel. By doing this, we further reduce the computational requirements, making it possible to run larger models with fewer resources. And here's the exciting part. When we combine sparsity with quantization, we create a powerful synergy. It's like having a map with fewer landmarks, and a car that runs efficiently on lower-octane fuel. This synergy could potentially allow for efficient local computation of previously unmanageably large models. In conclusion, algorithmic efficiency is a critical piece of the puzzle in making trillion-parameter models feasible for local use. It's about working smarter, not harder, and getting the most out of our computational resources. By combining algorithmic efficiency with advanced hardware and quantization techniques, we inch closer to making trillion-parameter models a reality. Software optimization plays a vital role in making large models feasible for local use. Diving into this world, we encounter two prominent strategies: quantization-aware training and developing advanced compression and decompression algorithms. Let's start with quantization-aware training. This approach is about improving techniques for training models in such a way that they are inherently more resilient to the effects of quantization. So, what does this mean? Well, imagine training a marathon runner. You don't just want them to run long distances. You want them to be able to do so on different terrains, under varying weather conditions. Similarly, quantization-aware training prepares models to maintain their accuracy and performance even when their parameters are drastically compressed, or quantized. This ensures that even heavily quantized models retain high levels of accuracy and performance. Next, let's talk about compression and decompression algorithms. These are the behind-the-scenes heroes that allow larger models to be stored and run on local devices. Think of them as the geniuses managing the storage room of a warehouse. They're the ones making sure that everything is packed as efficiently as possible without damaging the goods. Developing advanced algorithms to compress model parameters on the fly and decompress them during inference with minimal overhead is critical. It's like getting a flat-pack furniture delivery instead of a fully assembled dining table. It's the same end product, but one is much easier to get through the door. These software optimizations are not just about making the models fit. They're about ensuring that the models can run efficiently and effectively once they're in place. And that's key. There's no point in having a trillion-parameter model on your device if it grinds everything to a halt when you try to use it. Optimized software ensures that our hardware and algorithms can perform at their best, bringing us one step closer to our goal. No advancement happens in isolation. The AI community and open-source contributions are crucial to our journey. This statement rings true, especially when we're discussing the monumental task of making trillion-parameter models feasible for local use. The role of open-source tools and frameworks cannot be overstated. They simplify the process of quantizing and running large models by providing ready-made solutions and platforms. These tools, often created and maintained by AI enthusiasts and researchers, offer a collaborative space for sharing knowledge, innovations, and breakthroughs. They are the backbone of this ambitious endeavor, enabling hobbyists to contribute to the field without having to reinvent the wheel. Moreover, these platforms foster a culture of sharing and collaboration, accelerating innovation by allowing us to build upon each other's work. They democratize access to technology, breaking down barriers and empowering everyone to contribute to the future of AI. With the combined efforts of the AI community, we can make running trillion-parameter models on local machines a reality. So, can we make trillion-parameter models feasible for local use by hobbyists within a year? We've delved into the potential advancements that could transform this ambitious goal into reality. Advanced quantization techniques from sub-bit to adaptive and dynamic methods promise to shrink the memory footprint of these models dramatically. Hardware innovations like specialized AI processors and neuromorphic computing could make running these models on local devices feasible. Algorithmic efficiency, through sparse neural networks and efficient model architectures, also holds the key to reducing computational loads. Software optimization, including quantization-aware training and advanced compression algorithms, could ensure accuracy and performance don't suffer in the process. And let's not forget the vital role of open-source contributions and community efforts in accelerating these innovations. However, the challenges are substantial. Achieving such a leap within a year would require coordinated progress across multiple domains of computer science and engineering, and significant research investment. The task is daunting, but with the right advancements, we could be on the cusp of a new era in AI. The question is not if, but when.